In chapter 11 of mechanics for year 1, we're going to look at variable acceleration. Now, when we did chapter 9, that was called constant acceleration. So there's two different cases. When we used suvat was only valid if we had constant acceleration. So if you look at this first graph here, which is a VT graph, I could use suvat in this section here because the gradient is constant here. I could also use suvat in this section, and I could use suvat in this section. Okay, so I could split up into 3 different bits where there's 3 different sections of constant acceleration, and I could use suvat. However, in the real world, that's actually unlikely to happen. You could make a simple model which assumes constant acceleration, but more commonly it's going to be a variable acceleration, maybe something like this with a curve. It could even be that it looks similar to this graph, but maybe it's a bit more curved, like that. Because really, we can't instantaneously change acceleration. We can't instantly, so in 0 seconds, go from an acceleration of, say, 2 to an acceleration of -3. It's just not going to happen instantly. It's going to be a curve. So it's much more useful if we can handle variable acceleration. And the way that we do that is by describing either the displacement, the velocity, or the acceleration as a function of time, so in terms of t. And then we can use calculus, so differentiation and integration, to help us. So here I've got a curve half t cubed is my velocity. So this describes the velocity in this journey at any point in time. So what is the velocity after 4 seconds? So basically I'm putting in t equals 4 and seeing what value I get out for my velocity. So v is half times 4 cubed. So 4 cubed, 64, and then half of that is 32 meters per second. Or the other way around, how many seconds have elapsed when the velocity is 108? So this time we are putting in a value for v, maybe it's here, of 108, and then finding out what is the value of t that goes with that. So 108 equals half t cubed, so 108 times 2, and then we need to cube root it, which gives me 6. So after 6 seconds, the speed would be 108. Okay, so that's the important thing so far, is just that we can describe velocity or displacement or acceleration in terms of time, and we can find that value at any point in time. If we look at the gradient of this function, so remember we did VT graphs, the gradient of a VT graph is the acceleration. You can tell from here that the gradient is not constant. Maybe if we draw a tangent on to show that. So a tangent at the beginning might look like that. My next tangent, if I draw one later on, it's probably going to have to look a bit more like that. So you can see that it's getting steeper. The gradient of the line is getting steeper, so the acceleration is changing. Here's another example. So this time we've got the velocity. It's given by 2t squared minus 16t plus 24. We've got to find a few things out. So the first thing is the initial velocity. So that is when t is 0. That's what I mean by initial velocity. So v is going to be 2 times 0 squared minus 16 times 0 plus 24. So that is just 24 meters per second. Okay, that's basically like your y-intercept, isn't it? Part B, the values of t when the body is instantaneously at rest. Okay, sounds quite impressive phrase, and instantaneously at rest. That just means that its speed is 0 for a split second. Okay, so it's not come to a stop and then it's just sat there. It's just for a split second, its velocity is 0. This is a bit like in suvat when we did those problems where you threw a ball in the air and then it came back down. And we talked about how at the top of the arc, the velocity was 0. It's that sort of idea. So we want to solve, where does the velocity equal 0? Okay, and that's just a quadratic to solve. And you can solve that using whatever method you like. I'm just going to put it into my calculator. So my 2 times are t equals 6 and t equals 2. Those would be the 2 points in time. Part C, the value of t when the velocity is 64. So it would be when 64 equals 2t squared minus 16t plus 24. So I can do the same thing, but obviously subtract 64 from both sides and then solve that quadratic. So if I do that, I get t equals 10 and t equals minus 2. Now, obviously out of those two, t equals 10 is the relevant one. We're not going to deal with negative time in this instance. It might be useful to think about these problems in terms of the graph as well. So if we were to sketch this function just on a graph, it would look a bit like this. So I've just sketched it y in terms of x rather than v and t. But this is a graph of the velocity. And we can see the information that was on there before. So we can see at t equals 0 is at the point 24. We can see the velocity is 0 when t is 2 and t is 6. The one that we just worked out was when the velocity is 64. So we can draw on y equals 64. There's that line. One intersection is at t equals 10 and the other is at minus 2. Okay, so really it's just that this is following a quadratic curve, but we're only really interested in the positive x values because we obviously start counting at t equals 0. You could actually draw just a section of it on Desmos, so you could specify for x is greater than or equal to 0 and just draw a part of the graph. So this is really what we've modelled. Part D, the greatest speed of the body in the interval 0 to 5. Notice as well that it says greatest speed rather than greatest velocity. So it could be that it's a negative value, but a large negative value. So between 0 and 5, so let's just sketch this graph between 0 and 5 then. So let's do between 0 and 5, it's just going to be that bit there of my graph. Okay. Maybe I'll draw the whole thing as well. Okay. The reason it's just asked between 0 and 5 is because obviously this graph just keeps going up and up and up and up. So really the maximum speed, according to our model, would be infinite in theory, but that probably wouldn't be a very good model. So if we just plot it between 0 and 5 seconds, perhaps that's the only time where this model is valid. The greatest speed, we need to find basically the vertex of this graph, which is down here. Okay, at this point here, I don't want to reveal it just yet. So how do we find the vertex of a quadratic graph? Well, we've got lots of ways we can do that. We could complete the square, or we could differentiate it and find the turning point. So we could do it either way. Maybe we'll do it both just to show that we get the same answer. So for part D, if we complete the square first of all on this function, so I'm going to factor out the 2 first of all, just for the first 2 terms. Then I'm going to complete the square on the bit in the bracket. Then I'm going to expand that bracket out. And then just simplify it. What's that? 24 minus 32 minus 8. Okay, so according to this, my vertex would be at 4 minus 8. So that means that when t is 4, the velocity is minus 8, and that would be my minimum point on this graph, or the vertex. So the greatest speed would be 8 meters per second. Okay, let's check that on the graph. There we go, 4 minus 8. If we did it by differentiation, now we're differentiating v. Okay, so it's not going to be dy by dx, it's going to be dv by dt. Okay, change in velocity over change in time. Now if I differentiate this, I will get 4t minus 16. And then I want to solve that. Equals 0 to find the stationary point where the gradient is 0. So then t is 4. And then substitute it back into v. So that v would be minus 8 like we found before. Okay. So we get the same answer by doing it that way. Doesn't really matter which way around you do it. Okay, let's think a bit more about using differentiation to help us, because we used it there, but let's think about it a bit more carefully. So if I've got a distance time graph here, and I want to try and turn it into a velocity time graph like the one below, so this is for the same journey. Remember that the gradient, and we covered this when we looked at graphs in chapter 9, the gradient of an ST graph, that is going to be the velocity. Okay, so when I differentiate it, which obviously finds the gradient, I'm going to get velocity. So we could write ds by dt, so that's differentiating the displacement, because displacement is s. Sometimes they will use x instead, so you could write it as dx by dt. That gives me the velocity. Let's look at a few points on this graph to study that. In this section here, the gradient is basically a straight line, isn't it? This line is a straight line, so it has got a constant gradient. And you can see here in that section, the velocity is constant. Okay, it's always the same velocity, because in this section of the graph, the gradient is the same, so here the velocity is the same. In a different section of the graph, if I draw some tangents here, so if I look at the very first section, at the start it's very flat, and then it's going to get steeper. So if I drew a tangent here, it would be a lot steeper. So it's going from a low gradient to a higher gradient. Well, that's what's happening here. It's going from a low value to a higher value. After that, so maybe if I look between this point here and this point here, it starts off with a positive gradient. Then it's still positive, but quite a lot less. Then at the top, it's 0. It's like a turning point. So you've got a gradient of 0. And you can see this here, where my velocity is 0. So the gradient here is flat. So the gradient is 0. So my velocity down here is 0. And then after that, we get a negative gradient, so a downward slope. And you can see that the velocity is now negative. Okay, so this idea, the gradient of your distance time graph gives you your velocity time graph. In this last section, the gradient is 0, so the velocity is 0. Okay, because velocity is a differential of the distance, as the rate of change of the distance. Okay, you can think about it in terms of units as well. Distance is in meters, and then we differentiate it, so we're dividing it by time when we find the gradient. So meters divided by seconds, well, that's meters per second. If we now do the same process again and go to an acceleration time graph, so if I differentiate velocity, so dv by dt, or I'm finding the gradient of a velocity time graph, that will give me the acceleration. So the rate of change of velocity is your acceleration. Again, think about the units. So that's meters per second divided by seconds, which then gives me meters per second squared. Let's pick out a couple of points to look at. So maybe this first section, here we can see it is increasing and at a constant rate. It's a straight line. So the gradient here is the same throughout this thing here, and it's positive. So the acceleration is positive and the same. So the gradient here must be 4, hence I've got an acceleration here of 4. In this section here, the velocity doesn't change. So the gradient is 0, so the acceleration is 0. In this next bit, the gradient is negative. So this is a straight line going downwards, so the gradient is negative, which means the acceleration is negative. Then it goes back up, so we've got a positive acceleration. And then at the end, it doesn't change, so we've got a 0 acceleration. Okay. Now that we know that, and we know how these quantities relate to each other in terms of differentiation, let's have a look at a couple of problems. So a particle P is moving along the axis. At time t seconds, the displacement from the origin is given by this expression here. Find the velocity when t is 3. So we've got the displacement. So remember, to go from displacement to velocity, we need to differentiate it. So dx by dt will give me v. If we differentiate this, I get 4t cubed minus 32. And then we want to find it at t equals 3. So we can just substitute that in. So 4 times 3 cubed minus 32. Which is 76 meters per second. Part B. The value of t when p is instantaneously at rest. So remember, instantaneously at rest means the velocity is 0. We've got our expression already from the velocity. So we're looking to see when v, which is 4t cubed minus 32, equals 0. So that means 4t cubed is 32. So t cubed is going to be 8. So t would be 2. Part C. The acceleration when t is 1.5. So remember, to find the acceleration, I need to differentiate the velocity. Okay. I suppose I could write it as the second differential of displacement, because I need to differentiate displacement twice. So differentiate once to get velocity and then do it again. But basically I'm going to differentiate this here. So that would be 12t squared. And now I want to find the acceleration when t is 1.5. So 12 times 1.5 squared. 27 meters per second squared. Right, let's have a look at another example. So a child is playing with a yo-yo, and the yo-yo leaves the child's hand at time t equals 0 and travels vertically up in a straight line before returning to the child's hand. The distance s of the yo-yo from the child's hand after time t is given by this expression here, between 0 and 3. Justify the restriction 0 to 3 seconds. So I assume that this 0 to 3 seconds is the amount of time that the yo-yo takes to go all the way up and then all the way back down. If we plot a graph of this function, then it looks like this. And we're obviously starting at t equals 0, and that's just until t equals 3. Now you'll notice that this is the first time that it passes through 0 again. So it starts at distance 0, goes up, and then comes back down. And then at t equals 3, it's 0 again. So I think the justification here would be that this function is describing the distance. It's not about the displacement, it's just about the distance. So we're just interested in when it leaves the child's hand, which is at 0, 0, until it returns to the child's hand at t equals 3. We're not interested in what happens after that, because I assume they catch it rather than the yo-yo going through their hand or dropping onto the floor or something. So we're just interested in 0 to 3 seconds. Find the maximum distance of the yo-yo from the child's hand. So what we want is this point at the top of the graph. Now I could get it from this, but obviously we don't have this functionality in an exam. But we want to find the maximum point there. And the word maximum, that should make you be automatically thinking about differentiation and using that to help you. So what we've got is a cubic graph, and then we can find a local maximum point. So we're going to differentiate it and set it equal to 0, because at a stationary point the gradient is 0. So ds by dt, if we differentiate this, is going to be 0.6 plus 0.8t minus 0.6t squared. And then we want to set that equal to 0. Okay. So at stationary point. Now that's just a quadratic to solve, so I'm just going to solve it on my calculator. Okay, So my two values of t would be 1.8685. And the other value I get is minus 0.535. Obviously the one I want is this one. The minus 0.535 value, that would still be on the graph. That's going to be that other stationary point down here, look. But we're not really interested in that one. That's just part of the model. So we've got t, but we want to find the maximum distance. We don't want to find when it's at its maximum distance. We want to find out what actually is its maximum distance. So we need to put that back into s. So that's going to be 0.6 times 1.87 plus 0.4 times 1.87 squared, and then minus 0.2 times 1.87 cubed. When I do that, I get 1.213 meters. Let's check if that's right. 1.213 meters. Yes, 1.213 meters. So we can imagine it as like a graph like that and plot it and just think a bit of it as a cubic graph like we would have done in pure maths. Another interpretation of it is that it's when the velocity equals 0, because remember ds by dt equals 0. So this is when it's saying the velocity is 0. So it's going on its way up and then it's coming back down. So here it's got a positive velocity, and then on the way back down it's got a negative velocity because it's going downwards. So that's how we know that this point here must be when v is 0. So you could think of it like that as well. Okay, to have a bit of practice at using differentiation in this sort of problem, have a look at exercise 11c.